start recording the lecture. Okay. So in today's lecture, I'm going to talk about power transformers. This is the second main component in any power systems, and it is actually the component behind the infrastructure or the realization of modern power systems. So what I mean, without transformers, we wouldn't, have the power system that we see today. Like we wouldn't be able to deliver power over long distances. Like we wouldn't see high voltage transmission lines and so on. So the transformer is the main reason behind the power system that we see today. And I explained that before. Basically, transformers allow us to increase the voltage, decrease the voltage, and because of that, we can transfer power over, over long distances at high voltages. And this allows us to, of course, increase the efficiency, reduce the losses, reduce the voltage drop across transmission lines, and of course transfer power from different locations or even between countries. Okay, so today's lecture is about modeling single-phase transformers, and at the end we will solve an example, hopefully, if the time permits. Before starting today's lecture, I'd like to complete the last example in the generator modeling presentation. So in the previous lecture, we introduced a circuit that models synchronous generators. So let me quickly remind you about it. So in the previous lecture, we had this circuit. This was in lecture 8. That represents synchronous generators. So we have the resistance of the stator, we have the synchronous reactance, and the induced voltage, E. Of course, this circuit is per phase, so it is related to phase A. And the output voltage here is the terminal voltage, so I'm going to call it V. Okay. So this is the circuit that represents synchronous generators. So this is for synchronous generators. Okay. Okay, so this circuit, by the way, this circuit represents the steady state model of the synchronous generator. And as we explained before, this course is basically on steady state analysis, the power flow analysis of power systems. Okay, so we need a steady state model. This is what we talked about. But there is something missing here. There is something missing here. In synchronous generators, we do not just use the synchronous machine as is. So this model represents the synchronous generator without adding any controller, without controlling its voltage, controlling the output power. So this is just the very basic and simple model to represent a synchronous machine. But in reality, or in practice, any power plant has two main controllers. We have the automatic voltage regulator. We have two main controllers. The automatic voltage regulator, the AVR, and the governor, or the AGC, automatic generation control. This controller, I mean the automatic voltage regulator, controls the voltage magnitude. So here, this voltage is controlled using an AVR. So basically, what we do here, if I move this part, let's move it here. So this AVR measures the terminal voltage and compare it with a reference voltage, V reference. And we have here the AVR, and the AVR controls the DC voltage applied on the rotor windings. we know that there is like a DC winding here. This is the rotor winding. So the AVR controls this voltage. So by increasing the induced voltage E or decreasing the induced voltage E, we can regulate the magnitude of the voltage V. So here, this is V as a magnitude. Okay, and by controlling this magnitude, we can control, of course, the reactive power from the machine. This is something that we talked about in the previous lecture. We called it the power factor control, the power factor control. So this is the first controller, the automatic voltage regulator. Okay. The AGC, on the other hand, controls the input mechanical power to the machine, the input mechanical power. So, for instance, if this power plant or this machine is blazed or operates in a power plant, and this power plant is commanded to generate 50% of its power capacity, then we should do that using the governor. So the governor here deals with the mechanical system. So we know that we have the machine itself, the synchronous generator, and this synchronous generator is coupled to the prime mover, which is a turbine at the end of the day. So we have the turbine here. Okay, and we have the boiler, or the input mechanical power. Like this is the mechanical power. Or not, this is actually the thermal power, but the mechanical power is from the turbine. And we have the thermal power here, or the kinetic energy, or whatever. So I'm going to call it B thermal. Okay, so the governor controls the speed here. So the idea here is to keep the speed constant. We know that the speed, the mechanical speed, omega m, the mechanical speed, should be constant, because there is a relation between the mechanical speed and the frequency of the output power from this generator. Okay, they are proportional. So we need to control the mechanical speed in order to keep the frequency constant at 60 Hertz. Okay? So the governor basically compares the measured mechanical speed to the reference mechanical speed, and then it regulates, this is the governor, it regulates the input power. The input power. Okay, so this is basically how the governor works. It basically maintains constant speed for the machine. So we regulate some mechanical parameters using the governor, and the idea of the governor is to balance the input power to the output power. Okay, and at the same time we want to keep the mechanical speed constant. The other regulator that is used inside any power plant is the voltage regulator, and this voltage regulator controls the injected reactive power Q, in order to keep the voltage magnitude constant. So for instance, we keep it at the rated value, or we may introduce an increase in the terminal voltage to accommodate any voltage drop through the transmission lines. Okay, so this is something that maybe I didn't talk about in the previous lecture, but I wanted to elaborate on these two controllers, because they change how we model generators in a steady state analysis. If we consider the controllers into account, then this circuit, this linear circuit, it's a linear circuit. It's a voltage source behind an impedance. This linear circuit cannot be used directly in our steady state analysis, because those controllers are active 24/7. They are operating all the time, regulating the voltage, regulating the power from of the machine to keep the frequency constant. Okay, so those controllers have to be considered in our analysis, and I'm going to show you at the end of this course how we take these two controllers into account when we model synchronous generators for power flow analysis. Okay, so keep these two controllers for now, but I wanted to introduce them so that you won't be surprised when we model the synchronous generator differently or use a different nonlinear steady state representation for the generator to analyze the performance of our system. Okay, so this is just a quick reminder of what we have explained in the previous two lectures. In the previous lecture, we couldn't solve the last example. We stopped at part B. Okay, so let me go back to example 2. It's here. So in this example, we have a 3-phase generator, 50 MVA. The rated voltage is given. We have the synchronous reactance. So all the parameters are given. The resistance of the stator or the armature is negligible. Okay. The generator is delivering its rated power at 0.8 power factor lagging at the rated voltage to an infinite bus. And I explained in the previous lecture what is the meaning of an infinite bus. Okay, so we have this circuit. So we have the generator, we have JXS. The infinite bus has a constant voltage, which is the rated voltage, 30 kilovolt divided by √3, because we have to solve this circuit per phase. Remember, everything should be solved per phase. We have the power factor, we have S. The first part here is to determine the excitation voltage per phase E, and the power angle delta. So if we go back here to this example, we have the voltage, we have the power delivered to this infinite bus. The infinite bus is basically an ideal voltage source. We use it as a reference. So you can get S delivered to the infinite bus, and after that we know that this S is equal to 3 VA conjugate. We have the voltage, so we can get the current, and you apply Kirchhoff voltage law on this circuit. If you do that, you get EA, the excitation voltage. This EA has a magnitude and angle. Like it has a magnitude and angle. So the angle here is delta. This is the power angle because it is the angle difference between the excitation voltage E and the terminal voltage V. So we get delta, and what you get here is the phase voltage of E. If you multiply it by √3, you get the excitation voltage as a line to line. Okay. Okay. Now this excitation voltage, as we know, is proportional to the excitation current or the field current of the rotor. What is this field current? We know that the rotor has, if we go back here, the rotor is supplied by a DC source, and this DC source generates, let's call it EF. This is the field voltage, and it generates a field current IF, or the excitation current IF. So the excitation current or the rotor current is the current that generates the excitation voltage here. So the excitation voltage is proportional to the field current, the DC field current. This is a DC current, or DC, like DC by itself is actually direct current, so there is no need. It's just DC. Okay. Okay. In part B, the excitation is held constant. And this means the magnitude of E is constant. So what we do, we keep this current constant, and as a result, the magnitude of E remains constant. But the angle here, the power angle, could change. Okay. So we have this information. This is given or calculated, to be accurate, calculated from A. Then the delivering torque is reduced until the generator is delivering 25 megawatt. So previously the power was higher. The power delivered to the infinite bus was higher than 25, but we reduced the torque, the driving torque, until the generator is delivering 25 megawatt. So the new power, it is of course three-phase, is 25 megawatt. Okay. The question here is to determine the current, the stator current or the armature current, and the power factor. So how to get that? We can apply the complex power flow concept. We know that the generator is represented by a synchronous reactance, XS. The infinite bus voltage is given. We know that this is the rated voltage. It doesn't change because the infinite bus, as I told you, it's a source that can absorb or supply infinite power. And the word infinite is of course relative. It is not like absolute, like for example maybe 100 times the power generated by the synchronous generator. Okay, it is infinite theoretically, of course. So this voltage is constant. Okay, and we have the magnitude of E, but we don't know delta. The magnitude of E is known because we hold the excitation current constant. We know the power, so we can apply the complex power flow or the active power flow equation. We know that P, like in three-phase, is equal to EV over XS sine delta. And don't forget, if you are using the three-phase power, which is 25 megawatt, then you have to multiply by 3 here, because here we are going to use the phase voltages. Okay, so we know the active power. We have the excitation, the magnitude of the excitation voltage. Don't use here complex numbers. Don't use the complex voltage. This expression is given in terms of the voltage magnitudes. The voltage magnitudes. So because this is a common mistake I see when I mark midterm exams and final exams. Students here use the complex voltage. No, this is just the magnitude. Okay, same thing here. You divide by XS. The only unknown here is delta. Once you get delta, now you have the voltage here in phasor. You have the magnitude and angle. Now you can apply Kirchhoff voltage law and get IA. Okay, so E is equal to VA plus JXIA. You get A, and A you get here is complex, so it has a magnitude and angle. And the angle is theta. This angle is the power factor angle. So if you know theta, you can get the power factor. The power factor is cosine theta. Okay, this is part B. This is where we stopped last time. Now let's solve the last part, which is part C. If the generator is operating at the excitation voltage of part B, so now we know what this means. So this means the magnitude of E remains constant, just the magnitude. Remember, just the magnitude. What is the steady state maximum power the machine can deliver before losing synchronism? Before losing synchronism, what is the meaning of that? We want to get, so I'm going to go down. So this is part C. So E is constant. E is equal to E of part A, and it is constant. Now we know that the power is equal to 3E VA over XS sine delta. This is delta. This is P maximum. This is the maximum power. If you remember from the previous lecture, we draw the power curve, the power angle curve. So this is P delta. It is like this. This is the maximum power we can get which is equal to EA BA over XS times 3. And the power angle, the maximum power angle is 90 degrees. So delta maximum is 90 degrees. If the generator passes this operating point, then it will lose synchronism. What does this mean? It will not settle on a stable operating point. So before this point, like the generator has a stable operation theoretically to any point here. Okay, so for instance, if this is the mechanical power from the turbine, the intersection point, any intersection point here is stable. But if we pass this point, as I explained before, the generator will lose synchronism. So here, for instance, here, this point is no longer stable. So this point is unstable. This one is unstable. Okay, so delta, for any disturbance, delta will actually deviate and will not have any stable equilibrium point. And the generator will not be synchronized with other generators in the system. So synchronization here means it will not operate at the same frequency. It will not operate at the same frequency. And the angle difference between the voltage of our generator or the generator under study and the rest of the generators in the system, the angle difference is not constant, because delta here will actually keep bouncing. Keep here, like for any operating point in this range, delta will be bouncing. So this is the meaning of synchronization. In power systems, all generators are synchronized. They operate at the same frequency. This is one condition. And the angle difference is steady. The angle difference, if let's say we have generator here, another generator here, a third generator here, and so on. So if this generator, the voltage of this generator has an angle delta 1, this is delta 2, delta 3. If you look at the angle difference, delta 1 minus delta 2, or delta 2 minus delta 3, it should remain constant. It should be constant. But if one generator loses synchronism, then its angle will be bouncing, and this difference will no longer be stable. So this is the meaning of synchronism. So if we go back to the example here, the question is about the maximum power the machine can deliver before losing synchronism. We know that the maximum power happens when delta is equal to 90 degrees. Okay, I think I got the question. Yes, so always the angle should be lower than 90 degrees. And in practice, the range for operation is between, like the maximum range is between 30 and 40 degrees. So this is the maximum. We don't allow actually delta to exceed 45 degrees. So delta should be here because we have to keep a margin. So delta maximum here, this is, I'm gonna call it delta practical. Maximum is less than or equal 45 degrees. We have to keep a margin here, guys. This is a margin that we have to keep. Okay, for any sudden load increase or any large disturbances that may be applied or may actually disturb the system, we have to keep this margin to accommodate for any sudden changes in the loads. Okay, or a sudden outage in a line or another generator in the system and so on. Okay, so we have to keep a margin. Okay, so back to the example, we know that the theoretical maximum power that can be delivered by the generator happens when delta is equal to 90 degrees. So, and the value of this maximum power is given by this expression. Okay, we know the magnitude of the excitation voltage. We have it. We know the voltage of the infinite bus. We have the synchronous reactance, so you can get P maximum. Okay. Then we need to find the armature current corresponding to this maximum current. We need to find IA, the stator current. This is simple. We repeat the same steps we did in the previous part. P maximum happens when delta is equal to 90 degrees. So now we have E as a magnitude. We have its magnitude and angle. The angle here is going to be 90 degrees. We know it. And you apply Kirchhoff voltage law. We know that EA is equal to VA plus JXS IA. You got VA, which has the rated voltage, and its angle is 0. We have the voltage here. We have the magnitude, and the angle is 90. Now we can get IA. This is the last part of this example. Okay. So if you follow these steps, you should be able to get these answers. Any questions? Okay. Now let's talk about power transformers. This is another presentation. I think there is a question here. There is a question why after 90 degrees the system becomes unstable. This is something I explained in the previous lecture, so I encourage you to go back to my recorded lecture. We explained it based on the power balance. It's going to take maybe 5 or 10 minutes. I'm going to repeat it in today's lecture. But if you don't understand it, just let me know by email or approach me during my office hours. Okay. Should we use the theoretical value always or the practical value? Like if I don't give you if I don't refer to any practical considerations, then you have to use the default the theoretical value. So the theoretical value is the default value. Okay. Okay. Now let's talk about power transformers. In this presentation, I'm going to introduce transformers. I'm going to talk about the equivalent circuit of a power transformer, and we're going to talk about the transformer performance indices, and we have three-phase transformers, auto transformers. So there are many items or many topics to consider in this presentation. In today's lecture, I will stop after explaining the equivalent circuit of a power transformer, and then I will give you an example. Okay. Here in this presentation, we're going to talk also about regulating transformers such as auto transformers, phase shifting transformers, three-winding transformers, and so on. Okay. The project focuses on regulating transformers and how to correct the power factor. So I have already a draft for the project, which I'm gonna revise and review. Then I'm gonna post the project hopefully next week. So before the second lab, because I expect you to start working on the project immediately after the second lab. You will be able to solve the problems. You will be able to use transformers to control the power, control the voltage across a load, and so on. Okay. All the details about the project I'm going to explain hopefully next lecture or maybe the lecture after. So there will be two versions. And as I told you in the beginning of this course, that two students are allowed to work together. So groups of two students can work on the project. Also, I accept individual submission of the project report, and I will give you enough time to work on the project, maybe a month or more than a month, almost more than a month, I guess, to work on the project. So there is no rush. The GA is here. Also, I'm available if you have questions about the project. So the main idea of this project is to understand how regulating transformers affect the performance of power systems. Okay, so let's begin today's lecture. As you know, transformers transfer electric energy from one voltage level to another voltage level. So they don't manipulate the power. They don't manipulate the power. They are not active sources. They are not like generators. So generators can generate power, can inject power to the system. Transformers, on the other hand, ideally, the input power should be equal to the output power, but we change the voltage. We can step up or step down the voltage. These devices or these equipment are not electromechanical devices. So they are stationary. They do not rotate. They do not rotate. And the idea behind transferring power from the primary side of the transformer to the secondary side is done through magnetic coupling between the two sides. Okay. So as you can see, we have like a core, a magnetic core. We have like the primary, secondary winding, and based on the turns ratio, we can step up or step down the voltage. This is something that all of us know. Now let's talk about the construction of power transformers. And this is, again, this is an introduction. So the iron core is made of thin pre-insulated laminations sheets of silicon steel. So we have many laminations that make the core of the transformer. And the idea here is to reduce the induced current inside the laminations. Because any metal, if we have a closed loop, like this, made of metal, and you apply a varying magnetic field, then this closed loop will generate current. So we use laminations to increase the resistance of each lamination. We isolate those laminations to increase, again, the resistance and limit any eddy current that is generated inside each lamination. Okay, we use like silicon steel because it has high permeability or low reluctance to the magnetic field. Low reluctance to the magnetic field, because we need all the magnetic field generated by the primary coil to be coupling or to be transferred to the secondary coil in order to deliver the power from one side to another side efficiently. Okay. If we look at the core, we can have different types. We can have the core type. So this core type, as shown in this figure, it is constructed from a stack of U. This is the U, and I-shaped interchanged laminations. Okay. So as you can see here, we have the primary coil here. Okay, the primary winding is coiled on the U-shaped lamination, and we have the secondary winding coiled on the I-shaped lamination, like this. This is the first type. The second type is the shell type. Again, it is constructed from a stack of E and I shape. So this is the E, and then we have the I shape. This is is more efficient. This is more efficient than this one. Here, the eddy current or the leakage flux is higher. But here, the primary and secondary windings are wound on the same leg. So we have the same leg. So the leakage flux is minimal, because most of the flux generated by the primary winding couples the secondary winding, or enters or excites the secondary winding. And if there is any leakage, the leakage flux generated by the primary winding will tend to flow on the other legs of the E shape instead of flowing in the air here. Of course, we have some leakage flux, but most of the flux will tend to flow here and go back, and so on, like this. So this is more efficient. We have another structure called toroidal type. This is the most efficient core. So as you can see, it is built around a ring of shaped core. So this is the core. It is like a ring, and then you coil the primary, and then on the top of the primary you coil the secondary, as you can see here. So the closest ring shape eliminates air gap, so we have like less air gap, efficiency is higher, the leakage flux is minimal. Okay, so that is why it has high efficiency, small size, low noise, better voltage regulation. Because if you have low leakage flux, then the reactance of the winding will be low, and as a result the voltage will be better. I mean the voltage will be regulated better, because we will not lose any voltage drop across the reactance of the transformer. But the main disadvantage of this type, of course it has a higher cost compared to the other, and it has limited power capacity. So this one cannot be used in power applications, like power systems. So typically we use this one. Okay, we use this type in power systems. Okay, it is easy to manufacture, less cost, and it has higher power density, because we can easily cool down the coils. Like this core, has losses, like due to eddy current losses, hysteresis losses, and so on. So we have to think also about the fan and the ventilation mechanism to cool down the transformer when it deals with high power. This one, the toroidal type, is, as you can see, everything is dense. Like we have less air gap. We have, we don't have enough space to cool down the coil. And as a result, this one, if we use it for high power application, it will be, it will be heated a lot, and as a result, it will not be used. Like we cannot easily or efficiently cool down the coils and windings. Okay, so this is like an introduction to power transformers. We have different structures for cores. We have the core type, we have the shell type, we have the toroidal type. This one is mainly used for electronic devices, for power supplies. I mean, low power or low voltage power supplies, like maybe the power, for electronic circuits, maybe the power supply in your desktop computer, something like that. So this is not the one that we are gonna focus on. We are gonna mainly focus on these types for power applications. Like the windings, we know that we have primary and secondary. So this is the shell type. This is the E shape. So we have E, and as you can see, we have the primary and secondary, or secondary and primary. It doesn't matter. But from this picture, you can deduce which winding is high voltage and which one is low voltage. Can anybody tell? So which one is high voltage? Let me erase this. Use maybe a different color. So this one, we have two windings. Which one is high voltage and which one is low voltage? So this is, let's say, winding A and B. So can anybody answer this question? Which winding is the high voltage, A or B? If you don't get it, so for any transformer, whether the primary or secondary, it doesn't matter. So, but we have a side that has a higher voltage and a side that has a lower voltage. So for here, for instance, this is a step down transformer. If the primary is here and the secondary is here, oops, don't know what happened. Something wrong here. Okay. If this is the primary and this is the secondary, this is the high voltage and this is the low voltage winding, then this is a step down transformer. Step down transformer. But if this is the secondary, this is the primary, then this is a step up transformer, because the primary here is the low voltage and the secondary is the high voltage. So in this case, it will be a step up transformer. My question is, we have two windings. So let's say you are working in a transformer factory, and you open the chassis of the transformer, the cabinet of the transformer, and from the first lock here, one of the technicians asked you which winding is the low voltage winding. So if we have A and B, I don't know what is going on with the PowerPoint presentation. Let me clear. So this is A, and this is B. My question, which winding here is the low voltage winding, and which one is the high voltage? So we have A and B. Which one is the high voltage winding? Let me go back to the chat. The flat, okay, so one question here is, okay, so A, high voltage is the thinner cable, correct. So like the answer, the secondary is the low voltage. Like here, like secondary and primary, guys, doesn't mean that it is high or low voltage. The secondary and primary definitions are related to the source, where you connect the source. You connect the source always to the primary one. This primary winding could be the high voltage or the low voltage. It depends on where we place this transformer. But I think, yeah, Luke answered the question correctly. So the high voltage winding is the one that has a thinner cable, because when we have high voltage, the current will be low. And as a result, the cross-section area of the wire will be thinner or smaller. So B is the high voltage. A, it has, as you can see, the cable or the wire is thicker. So B should be the low voltage, because at low voltage, the current will be high. Okay, so if you look at this figure is basically a cross-section area. A cross-section area of like made here. We have the primary, we have the secondary. Like here we have laminations, as you can see, different laminations, and all wires here are isolated. They are isolated by paper or synthetic insulating materials. So these wires are not, you know, you may look at it and see the color of the metal, but they are isolated. They are isolated, and most of the transformers get damaged when they get heated, and the insulation here is broken down. Okay, so we may have a short circuit between 2 turns or 3 turns or 5 turns, or something like that. And in this case, the transformer has to be disconnected. We may, you know, coil the winding again or replace it with a new transformer. Okay. Okay. Now let's revise, let's review the transformer action. There are 3 stages. So we have to apply a changing current to the primary winding to have alternating magnetic field on the core of the transformer. In synchronous machines or synchronous generators, the current of the rotor was constant. It was a DC current. It was a DC current, like this. The stator was stationary. So if we do not rotate the core of the machine, of the synchronous generator, then we will not have alternating magnetic field. That is why we have to rotate the rotor, because the field generated by this DC source is constant. If everything is stationary, the field of the rotor is constant. So we have to rotate the rotor in order to have alternating magnetic field applied on the stator windings. And in transformers, we don't have any rotation. We don't have any rotation. So for transformers to operate, we should apply AC current. So transformers cannot work with DC current, and that is why in the beginning, in the beginning of power system, maybe 150 years ago, the battle was between DC and AC current or AC systems, and the AC systems, won at the end of the day because of the transformers. We can increase or decrease the voltage of in AC systems, but for DC systems we can't. Nowadays, as I told you, we have DC transformers, and the idea is very simple. If we use power electronics, let me go back to my notes. This is, of course, lecture 9. So if you have a DC system or a DC bus, you need a DC to AC inverter, okay, DC to AC inverter, and then the output here will be AC, but this AC can be at high frequency, so we connect here high frequency transformer, high frequency transformer. The output here will be AC, again at high frequency, but depending on the turns ratio of this transformer, we can increase the magnitude of the voltage or decrease it, and then we put a rectifier, a simple rectifier. This is a rectifier, okay, to output DC. Okay, so using this configuration, we can construct a DC transformer, and also we can have the insulation. So this high frequency transformer is basically a transformer. So we have insulation between the two sides. We can use other power electronic converters. For instance, you can use the boost converter. We can directly like increase the voltage or decrease the voltage. So if you use a boost converter, I'm not sure if you attend Dr. Carr's course, I mean the power electronics course, or not, but we can use directly a boost converter or a buck converter to manipulate the voltage, the input voltage. But those converters do not provide isolation. So the primary side is coupled to the secondary side electrically. In AC transformers, the primary and secondary side are not coupled electrically. So we have this insulation, which of course is important for safety. So for AC transformers, we have the primary, secondary, and they are connected magnetically. So we have isolation. So the grounding here is different than the ground here. Okay. Okay. So this is just a quick note. But if we go back to AC transformers, we need AC current. Okay. This AC current will generate alternating magnetic field, and as a result, it will induce voltage in the secondary winding. And then when a load is connected, the power will be transferred from the primary to the secondary side. This is basically the transformer action that you have studied before. Okay, now let's consider ideal transformers. So in ideal transformers, we assume that the core itself is ideal. It doesn't have any reluctance to the magnetic field. And this means it has infinite permeability. The reluctance of the core is zero. It doesn't have any leakage flux. So all the flux generated by the primary side will be coupling entirely the secondary coil. Nothing is lost. Okay? We don't have any resistance for the winding. It's an ideal winding. We don't have core losses like eddy current losses or high stresses losses. So as a result, if we consider this as to be the ideal part of the transformer, the input power should be equal to the output power. And here we can define the turns ratio N1 to N2 to be 8. Now, let's look at the induced voltage. So if the flux generated is expressed by this equation, and it has to be sinusoidal because it is proportional to the current of the on the primary side. The current here is AC, so the flux should be AC. And you apply Faraday's law, you can get V1, the voltage here, which is equal to E1, because there is no voltage drop in between. There is no resistance, there is no leakage reactance, and so on. This is going to be V2. You can get it also using Faraday's law. And in RMS, you can divide this maximum voltage by √2 to get the RMS value. And at the end of the day, the voltage ratio is equal to the turns ratio. This is something that every one of us knows. Okay. Now, let's look at the current ratio. We can get the current ratio using the power balance. We know that this is an ideal transformer. This is an ideal transformer. So the input power should be equal to the output power. And we know the voltage ratio. So if you know the voltage ratio and you know that there is no power losses for ideal transformers, then we can get the current ratio. Another way to get the current ratio is to draw the magnetic circuit of the power transformer. On the primary, we have this source. This is the magnetic source, which is the number of turns times the current. On the secondary side, also, we have the number of turns times the current. We get the source on the secondary side. The reluctance is 0. We don't have any reluctance because this is an ideal transformer. So the summation of MMFs should be equal to 0. This is like Kirchhoff voltage law, but we apply it on the magnetic circuit of the transformer. So you get the same current ratio that you get from the power balance equation. Now let's talk about the dot convention. Okay, so the dot convention is a way to indicate the output current or the direction of the output current on the secondary. The direction of the secondary current or the output current on the secondary side. Okay, so for example, if we have this transformer, look at it. If you look at this, the current of the primary is entering the dot, this dot, so it will flow in this direction, and then this direction, then direction. If you apply the right-hand rule, the current rotates this in this direction, so the magnetic flux should be up. Look, the current flow in this direction, so the magnetic flux should be up. So the flux generated by the primary coil should have this direction. Okay, so it rotates upward, and as a result, it will be circulating like clockwise. So this is the direction of the flux. Okay. Now this secondary has to generate, according to Faraday's law, has to generate a flux that opposes the flux generated in the primary or by the primary coil. So it has to generate a flux in this direction. Again, let's apply the right-hand rule. If you have the flux generated by the secondary in the upward, then the current should be in this direction. I hope you can see my hand, like this. So this means if we need to generate a flux in this direction, the current of the secondary has to be in this direction. And that is why we add a dot here to represent the direction of the output current on the secondary side. If you coil the secondary winding in the opposite direction, if you coil the secondary in the opposite direction, and you can try it at home, of course, then we have to place the dot here. So the current should be out from the bottom, not from the top. Okay, so the direction we coil the secondary side determines where we put this dot, and the dot indicates the direction of the output current on the secondary side. Okay. Okay. Now let's see what happens when this ideal transformer is loaded. So we connect an impedance on the secondary side and see what happens to the transformer, and particularly how this impedance is seen from the primary side. So we are interested in getting the equivalent impedance on the primary side. Okay, so for ideal transformer, we know that V1 over V2 equals N1 over N2. So we can write V1 in terms of V2. Same thing for I1. We can write it in terms of I2 times the reciprocal of the turns ratio. Okay. Now we know that Z1, okay, Z1, I mean the impedance seen from the primary side is the voltage divided by the current. So V1 over I1. Now we can replace V1 using these two equations. So we can get V2 over I2 times N1 over N2 squared. We know that V2 over I2 or IL gives us the impedance of the load. So this is Z load. So the impedance seen from the primary side is equal to the load impedance times the turns ratio squared. This is how we transfer the impedance from the secondary side to the primary side. Why we need to do that? We need to do that to solve the circuit, solve the power flow problem. Like if you look at this transformer, there is actually a gap here. There is like a magnetic circuit. We have to get rid of this magnetic circuit in order to analyze the transformer. So one way to do that is to transfer the circuit on the secondary side to the primary side and start analyzing the circuit as if there is no magnetic coupling. Okay. So ZL dash or prime represents the image of the load impedance as seen from the supply side or the primary side. Okay. Now let's look at non-ideal transformers. So what are the characteristics? The primary and secondary windings have resistance. Any coil has a resistance. There is flux leakage. There is flux leakage, of course. The core itself is not ideal. The core has finite permeability, so it has a reluctance. The reluctance of the core is not zero. There is a drop in the flux or flux needed by the core in order to magnetize the secondary winding. There are core losses, high stresses, and eddy current losses. Okay. So for the copper losses, I mean to integrate the resistance of the coil, we can get the resistance out. So R1 and R2 represents the copper losses of the primary and secondary windings. Okay. The flux leakage, I mean phi L1 and phi L2, can be represented by reactances, as you will see in the next slide. Okay, so here we know that the flux linking the primary winding is given by this equation. So it has a flux that flows only in the core. So look, the flux generated by the primary has two components: the flux that flows entirely in the core, which was the previous case for ideal transformers, and there's a leakage flux. So we can write it as the summation of two components. Now, if we apply, apply Faraday's law and write the voltage equation. So V1, the V1 here is the supply voltage. E1 is the voltage on the ideal transformer. The voltage on the ideal transformer, the induced voltage. Okay, the induced voltage. This induced voltage is linked only to the flux inside the core, not the leakage flux, as we did with ideal transformers. So we have V1 that is equal to R1 I1 plus N1 d phi 1 by dt. Phi 1 has two components: the leakage component and the core component. This core component represents the induced internal voltage, E1. The second component here can be replaced by I1L1. So the leakage flux, as I mentioned, can be represented by a reactance or an inductance. And this inductance is known to be the leakage inductance. So at the end of the day, we can write this equation for V1. This is the supply voltage. We have the induced voltage, and we have voltage drop across the leakage, inductance, and the resistance. And same thing for the secondary winding. This is the time domain model. I mean, this is the differential equation model. Okay, that is applicable for transients and also steady state. But in the phasor domain, the derivative is represented by j omega. Okay, and as you can see, V1 is equal to E1 plus a voltage drop across an impedance, the impedance of the primary and the impedance of the secondary. So Z1, the impedance of the primary is R1 plus j omega L1. Okay, this is how we represent the losses, the copper losses, and the leakage flux of the transformer. Now, how to represent the losses, the core losses, the hysteresis and eddy current. So for we have like heat dissipation, like we have two elements to to represent the core effect. Okay, we have heat dissipation. This heat dissipation is actually active power. It is active power that the transformer loses. So this heat dissipation is represented by a resistance. And this resistance is proportional to the voltage applied on the primary winding, not the current. Not the current. Okay? So that is why we have to connect this resistance in parallel, not in series. Not in series, because it is proportional. It depends, I mean, its power consumption depends on the voltage of the primary, not the load current. We have another component for the core, which is the magnetization reactance. This magnetization reactance represents, you know, the reluctance of the core. The core is represented like in the magnetic circuit like this. N1, I1, N2, N2, and there is a reluctance here. This reluctance consumes part of the current in order to accommodate any losses in the MMF. There is losses in the MMF across this reluctance, similar to like the voltage drop. Voltage drop, we need also a current component that compensates for this reluctance of the magnetic circuit of the transformer. So this is how we represent the transformer. We have a shunt element or a shunt impedance representing the core losses, the hysteresis losses, the eddy current losses, the heat dissipation inside the transformer. We have a reactance representing the losses in the core, I mean the magnetic flux lost by the core itself, the reluctance of the core itself, and we have the rest of the transformer. We keep this part to represent the ideal part of the transformer. So here we have the transformer action, assuming no losses, no leakage flux, and so on. And here, as you can see, E1 and E2 are related to each other by the turns ratio, N1 to N2. Okay, the rest of the parameters are added to the circuit in order to have a realistic representation for V1 and V2, the secondary voltages, not the induced voltages or the internal voltages that are inside the transformer itself. Okay. Now let's look at the exact phasor diagram. Okay, we can write two equations for V1 and V2, as you can see. So you apply Kirchhoff voltage law on this loop, another equation for this loop. We can apply Kirchhoff current law at this node. So we know I1, okay, this is I1 or the supply current. So this is I1 or the supply current is equal to IE, the excitation current consumed by the transformer core, and we have I2 dash. What is I2 dash? I2 dash is the load current divided by A. So it is the image of the load current when it is transferred to the primary side, and we know that we can transfer the current from the secondary side to the primary side using the turns ratio. So if you remember, I2 of the ideal transformer over I1, or let me write it the other way. I1 over I2 is equal to N2 over N1, or 1 over A. So I2 dash is I2 dash, or the current seen here is I2 over A. This is what you see here. So we got an equation for I1. IE, the excitation current, is divided between RC, the core resistance, and the core reactance. So this is IE. Basically this current will be divided like this. And we have the other relations. One thing that I want to talk about is the relation between IM and E1. Okay, so E1 is perpendicular to the magnetization current, similar to what we explained in the synchronous generators. Remember, the current of the stator generates magnetic field in the direction, in the same direction of the stator, and as a result, the induced voltage should be lagging or leading by 90 degrees. There is like 90 degrees between the induced voltage and the magnetization current that results in the induced voltage. This is like a rule in magnetic circuits. Okay, so now I want to explain the phasor diagram. So we start from the load. Because the load voltage has to be regulated. So and we know that the load power or the load current. So we better start from the load. So we have V2. Let me use a pointer. So this is V2 of the load, and I2 is the current consumed by the load. And typically there is like lagging power factor. So θ2 is the power factor angle. Okay, I2 is related to I2 dash using the Turner's ratio. So I2 dash should be in phase with I2, but maybe shorter. Or smaller. The vector should be like smaller or higher. It depends on the transformer action, whether it is step up or step down. But I2 dash should be in phase with I2. Okay. This is I2 dash. Okay. Now we can get E2. We need E2 to move from the secondary to the primary. So how to get E2? We know that E2 is equal to V2 plus this voltage drop. So E2 is equal to V2 plus I2R2 plus J I2X2. You get E2. If you have E2, you can get E1, because E2 and E1 have the same direction, but one of them is higher than the other. So here E2 is lower than E1. Okay, so we got E1. We have E1, we have I2 dash. These are the beginning point, or the starting point, to analyze or to draw the phasor diagram of the primary circuit. So you have E1 and we have I2 dash. Okay, in order to get V1 we need I1. So what is the equation of I1? I1 is equal to IE plus I2 dash. We have I2 dash here. How to get IE? We can get IE using E1. So IE is equal to E1 divided by RC. This is the first component of IE, and the second component is IM, and IM is E1 divided by JXM. So this is IE, and this is IM, and this is IC. Okay, IE is equal to IC plus IM, and this is how we get IE. Okay, so IC is IC, this IC, let me use the laser pointer again. So IC is IE divided by RC. So it should be in the same direction of E1. So IC is E1 over RC, and RC here doesn't change the angle of E1, so IC should be in the direction of E1. IM should be lagging E1 by 90 degrees. That is why you see IM here. The vector summation of IC and IM gives us IE. So you have IE. If you add IE to I2 dash, which we got from analyzing the secondary circuit, you add IE to I2 dash, you get I1. Once you get I1, you can calculate the voltage drop across R1, across X1, and you get V1 here. So this is the detailed phasor diagram of the transformer exact model. This is the detailed phasor diagram of the exact model. Okay. So as you can see, there are steps. We start from the load, we move to the ideal part of the transformer, and then we get I2 dash, and then the excitation current, and then we go to the supply. Okay, so there are many steps. If you solve it by hand, you will find that there are many steps that we have to go over. Okay, let me see if you have any questions. Okay, no questions. Guys, if you have any questions, please let me know. Okay, so let's continue. Okay, now let's talk about referring quantities from one side to another. So if we have the turns ratio N1 to N2, this is A. And if you want to refer voltage, current, and impedance from this side, the secondary side, to the primary side, for voltage you have to multiply by A. For current you have to divide by A. For impedance you multiply by A squared. If you want to move from the primary side to the secondary side, then you do the opposite operations. So here, instead of multiplying by A, you divide by A. Here you multiply by A. Here you divide by, if you want to transfer Z1 to Z1 dash, you divide by A squared. Okay, and as a result, we can get two equivalent circuits for transformers. One circuit as referred to the primary side, so all components on the secondary side are referred to the primary side. As you can see here, everything is referred, the resistance, the reactance. Okay, or we can refer the primary circuit to the secondary side on the other way. Okay, these are the two equivalent circuits. Now I want to talk about, I want to solve the first example, so I'm going to discuss it. We have still 7 minutes. So in this example, we have a single phase transformer. We got the parameters R1, X1, R2, X2. We have RC, XM referred to the primary side. So I have to tell you the side in which the core parameters are calculated or referred to. So RC and XM are referred to the primary side. This is the default side, by the way, for the core parameters, RC and XM. The transformer delivers 20 kilowatt at 0.8 power factor lagging on the low voltage side. Okay, so we have the voltage across the load. It is given. Find the primary terminal voltage using the exact circuit model. So I'm going to discuss with you the steps, and this is the final answer. So I encourage you, of course, to follow the steps and try to reach this final answer. Okay, so here, this is the first example. Example number 1. We have the exact model like this. This is R1, JX1, R2 should be dash, because now it is, we are trying to get the primary voltage, so it is better to refer everything to the primary side. So instead of using the resistance on the secondary side, we should refer it to the primary side. So we have R2 dash, we have X2 dash. Here, XM and RC already calculated or given, refer to the primary side. So we don't need to transfer them and do it or do anything. The turns ratio A is 440 divided by 220, which is 2. So this is A. R2 dash and X2 dash. So R2 dash is equal to R2 times A squared. X2 dash is X2 times A squared. Okay, this is how we get these two things. Here, this is V1, and this voltage here should be V2 dash. V2 dash is equal to A V2. So what is V2? V2 is given. V2 here is 200. Let me decrease this. V2 is 220. So V2 dash is 220 times 2. So it is 440. And this voltage should be like phasor voltage. It should have an angle. Okay. The idea here, as I told you, since we need to control the voltage across the load, so we start backward. We start from the load and move from the load to the source. We start from the load and move from the load to the source. Why? Because we want the voltage across the load to be regulated. So the voltage here is known, and the power consumed by the load is known. So we know everything on the load side. So why not we start from the load side and move backward to the source to see what voltage at the source we need to keep the voltage regulated on the load side. Okay. Okay. So if V2 dash is given, or sorry, V2 is given, we can calculate V2 dash. Let's give it a 0 angle to be the reference. Okay. We have the power delivered to the load, and the power, by the way, is not referable. Like the power doesn't change if we refer the circuit from the primary to the secondary or from the secondary to the primary. So the power is given. So S2 is equal to the power divided by the power factor, and the angle here is cos inverse the power factor. The power is 20 kilowatt. This is 20 kilowatt, and the power factor is 0.8. Okay, find the primary terminal voltage using the exact circuit model. Okay, so you can calculate I2 dash. I2 dash is equal to S2 over V2 dash conjugate. If you get I2 dash, which is here, this is I2 dash. You can get the voltage across the shunt element, which is E. The voltage here is E1 or E2 dash. So E1 is equal to V2 dash plus I2 dash times R2 dash plus JX2 dash. Once you get E1, you can get the current here, IE. So IE is equal to E1 over RC plus E1 over JX M. You have IE. If you have IE and you have I2 dash, you can get the current here, I1. I1 is the summation of IE and I2 dash. So I1 is IE plus I2 dash. Once you get the current of the primary winding, you can get V1. So V1 is equal to E1 plus I1 R1 plus JX1. Because here you got the voltage. So if you add this voltage to the voltage drop across this impedance, you get V1. And this is how you solve this example. Let me move. Yeah, I think, yeah, the lecture is over. Do you have any questions, guys? Okay, so if you don't have any questions, thank you for attending today's lecture. Always available during my office hours. Also, the GA is available. If you have any questions, don't hesitate to email us or communicate with us during the office hours. Okay, thank you. Thank you. Have a good day. Bye.